Calculating entropy changes. How do we calculate entropy changes for solids, liquids, and ideal gases? We had previously defined two intensive properties, temperature and pressure. Temperature was defined by the expression that 1 upon T is equal to the partial derivative dS by du with m and v constant. We can divide both the numerator and the denominator by m, the mass of the system. This gives us a partial derivative in terms of the specific entropy and the specific internal energy. Similarly, pressure was defined by P upon T equal to the partial derivative dS by dV holding m and u constant. Again, dividing by m, we get a partial derivative in terms of the specific entropy and the specific volume. Now, temperature and pressure are both intensive properties. So over here, we have written them as functions of all intensive properties. Let us start with the state postulate that S is a function of U and V. Differentiating that, we get that ds is the partial derivative dS by du times du plus the partial derivative dS by dV times dV. Now we'll recognize these two partial derivatives. The first one is just 1 upon T. The second one is just P over T. Substituting that, we get a very important equation, which is known as the Gibbs equation. And this says that ds is equal to 1 upon T times du plus P upon T dV. The importance of this equation is that it gives us the change in entropy as a function of variables that are all easy to measure and familiar to us: the pressure, temperature, internal energy, and specific volume. Let us apply the Gibbs equation to calculating entropy changes in incompressible substances. And we are assuming that all liquids and solids are incompressible substances. For an incompressible substance, the volume is constant, and therefore dV becomes 0. Also, we had shown that for an incompressible substance, the specific heats Cp and Cv are the same, and therefore we drop the subscript and just write C. du for an incompressible substance is C times dt. Substituting this into our expression for the entropy change, ds is equal to C times dt divided by T. If we take this expression, we can then integrate it so that delta S would be the integral of C times dt over T. If we assume that the specific heat is constant and has some average value C average over the temperature range from T1 to T2, we can then take that outside the integral. Integrating it, we get that delta S is C average times ln T2 upon T1. We can write the entropy change, therefore, as delta S is equal to C average times ln of T2 minus ln of T1. And we'll recognize the similarity between the entropy change and the internal energy change, because delta U is C average times T2 minus T1. So the internal energy change is the specific heat times the change in temperature. The entropy change is the specific heat times the change in the log of the temperature. Now, we can also apply the Gibbs equation to calculate entropy changes for ideal gases. For an ideal gas, we know that du is Cv times dt. We can also use the ideal gas equation to say that P upon T is equal to R upon V. We substitute du into the expression for ds, and we also substitute P over T in the expression for ds. And that gives us that ds is equal to Cv upon T times dt plus R dV upon V. We can take this expression and integrate it. So we get the integral of Cv dt upon T plus the integral of R dV upon V. If we assume that Cv is constant, we can take it outside the integral. So delta S becomes Cv ln of T2 upon T1 plus R ln of V2 upon V1. So this expression gives us delta S as a function of the temperature and the specific volume. It may be more convenient to have pressure and specific volume as the independent variables rather than temperature and volume. We can use the ideal gas equation, therefore, to say that T2 upon T1 is equal to P2 upon P1 times V2 upon V1. And we'll substitute this into an expression for delta S. Doing that, we get that delta S is equal to Cv ln of P2 upon P1 plus Cv plus R times ln of V2 upon V1. Now for an ideal gas, we know that Cp is equal to Cv plus R. So let us replace Cv plus R by Cp, and the expression that we get is delta S is equal to Cv ln P2 upon P1 plus Cp ln V2 upon V1. Finally, it may be more convenient to have pressure and temperature as the independent variables. So let us start again with the Gibbs equation, and we'll write it in the form that Tds is equal to du plus Pdv. Let's combine that with our definition of enthalpy, that H is equal to U plus PV. Differentiating this, we get the dH is equal to du plus Pdv plus Vdp. Rearranging this equation, we get du plus Pdv is equal to dH minus Vdp. Now the left-hand side of this is the same as the right-hand side of the Gibbs equation. So substituting this back into the Gibbs equation, we get that Tds is equal to dH minus Vdp. And we can think of this as an alternate form of the Gibbs equation. So we write ds is equal to dH upon T minus V upon T dP. And we have the change in entropy as a function now of the enthalpy instead of the internal energy. So if we start with this equation, and we know that for an ideal gas, dH is equal to Cp times dt. Let's substitute for dH and also use the ideal gas equation that V upon T is R upon P, and substitute that also into our equation for ds. So we get that ds is Cp times dt upon T minus R dP upon P. We can integrate this. So now delta S is the integral of Cp dt upon T minus the integral of R dP upon P. Assuming Cp is constant, we get that delta S is equal to Cp ln T2 upon T1 minus R ln P2 upon P1. And so this is our third equation for delta S. And in this, the independent variables are the temperature and the pressure. Now, what if we don't want to assume that Cp is constant in this equation? In that case, let us take that integral with Cp in it, and we'll split it into two. The first of these integrals is from some arbitrary reference temperature, Tref, up to T2. And we subtract from that an integral, which is from Tref to T1. Again, when we take the difference, the term in Tref would cancel out, so it doesn't matter what reference temperature we use. Now, let us define a new variable, S0. This is a function of temperature, and it is defined as the integral from Tref to T of Cp dt upon T. So our expression for delta S, we can now write it as S0 of T2 minus S0 of T1 minus R ln of P2 upon P1. Now we can calculate values of S0 by integrating out from Tref to T times Cp dt over T. We can substitute polynomial functions for Cp, and these are derived from experimental measurements, so the polynomial function is fitted to experimentally measured values of Cp. Also, let's assume that S0 is equal to 0 at Tref is equal to 0. This is a convenient reference temperature. Doing this, we get what are known as the air tables. So the air tables also list values of S0 as a function of temperature. So if we want to calculate delta S, we can look up the values of S0 at the two temperatures T1 and T2 directly from these air tables, substitute the values in our equation, and we can use that to calculate a more accurate number for delta S, where we are not assuming that Cp is constant. To summarize, we have derived the Gibbs equation ds is equal to 1 upon T du plus P upon T dV. We can integrate the Gibbs equation for an incompressible substance, in which case the change in entropy delta S is equal to C average times ln T2 upon T1. For an ideal gas with constant Cp and Cv, integrating the Gibbs equation gives us three different equations. The first, delta S, is a function of T and V, which is equal to Cv ln of T2 upon T1 plus R ln of V2 upon V1. The second, delta S, is a function of P and V, which is equal to Cv ln of P2 upon P1 plus Cp ln of V2 upon V1. The third is delta S as a function of T and P, which is equal to Cp ln of T2 upon T1 minus R ln of P2 upon P1. And finally, if we don't want to assume that Cp is equal to constant, then we can look up the values of delta S from the ideal gas tables, in which we look up the values of S0, which is a function of temperature alone, and we substitute that into our equation, where S0 of T2 minus S0 of T1 minus R ln P2 upon P1.